Okay, good evening to everyone. So, so today we will discuss quantifiers. So, formally, uh, first I will tell the definition of quantifiers. So, it means the quantity. Okay. For example, you can see here. Uh, Statements involves words indicates quantity such as all, some, none, or one. Okay, so these are all the statements indicating what the quantity. So actually, they answer for the question how many. Suppose we are asking how many students in your class got uh, S grade in M3. So maybe you can tell some of the students got S grade in M3. Okay, so since such words indicate quantity, so they are called quantifiers. An analysis of mathematical sentences involving quantifiers indicates that the main two quantifiers are all and some, where some is interpreted to mean at least one. So sum is equivalent to at least one. Okay, here you can see some of the sentences. Some men are tall. All birds have wings. No balloon is perfectly round. There is a real number less than 10. Okay. So instead of writing some men are tall, so you can write restate by there is at least one man. Okay, there is at least one tall man. So both of them are equivalent. Some men are tall is equivalent to what? There is at least one tall man. Similarly, no balloons is perfectly round. So it's same as all balloons fails to be perfectly round. Okay, so this no balloon is perfectly round is same as what? Here no balloon perfectly round. Here all balloon fail to be perfectly round. Okay. Next, there is a real number less than 10. So there is a real number. Instead of there is a real number, at least one real number less than 10. So 4 and example 4 and these statements are equivalent. Okay. So look at first the quantifier all. So this quantifier all is called universal quantifier. We shall denote it by the symbol every x. Okay. For example, you should write. Okay. Now, okay. So here, so I told that we shall symbolize, okay, for universal quantifier for every x, okay, wow. So you can write for every x, or you can write bracket within bracket for every x. So both of them are same meaning. Next, the symbol for every x represent each of the following phrases, since all have essentially the same meaning. For all x, for every x, for each x, everything x is such that, each thing x is such that. For these, okay, wow, for these you can use what? The universal quantifier every x. Next one, sum. This is called existential quantifier. The notation for existential quantifier is, you should write like this. Actually, they call it is which is reversed E. Okay, reversed E. So this is where you can write there exists X. Or similarly, you can write what? There exists X within bracket like this. Okay. So it represent each of the following phrases. For some x such that, there exists an x such that, there is an x such that, there is at least one x such that. So for all, we can use what? There exists x. Okay. Now we are going to write the following statements in symbolic form. Sometimes these type of questions are asked in 2 mark question. Something is green, everything is green, nothing is green, something is not green. Okay, the statement 5 means there is at least one x such that x is green. Something green is equivalent to, you can say like this, there is at least one x such that x is green. Sixth one is everything is green. So instead of writing like this, you can write what? For all x, because everything. So that's why for all x, x is green. Nothing is green. So here, for all x, x is not green. Okay, so nothing is green. And the something is not green. So 8, something is not green. So there is at least one x such that x is not green. So from these sentences, first I will convert these 4. And then from the first one, there is at least one x such that x is green. So first I will write g of x, x is green. So then I'm going to write this sentence, there is at least one. So there exists x, okay, g of x. That means there is at least one x such that what? X is green. Again, sixth one, everything green. Everything green means for all x, g of x. G of x means x is green. Again, 7. 7 is what? Nothing is green. For all x, x is not a green. Okay, for all x, x is not a green. Next, 8. Something is not green. Something is not green means there is at least one x. X is not green. So there is at least one. So there exists an x such that x is not green. So first you should understand these concepts. So next I will go to next slide. Okay. So here I'll start from the third sentence. So not all true. So not all true means same as what? At least one is false. Okay. Similarly, not all false means at least one is true. Okay. Now, for the third one, I'm going to write this here third. Okay. Not all true means not all of them are true. Okay. Negation of every x p of x. That means not all of them are what? True. Is equivalent to what? At least one is false. At least one is false means there exists x negation of p of x. Okay. Now, fourth one, not all false. Instead of not all false, negation of every x negation p of x. Not all false. Okay. False negation p of x. Not all negation of every x is equivalent to at least one true. At least one true means there exists x p of x. Okay, so 3 and 4 are over. Now, all true means what? Means same as what? All true is same as none false. So, the first one is negation of this one, third one. You can see here, not all true. Not all true. What is negation? All true. So from the third length, I'll go to the first one. So if I take negation of this statement, I will get this portion. Similarly, I should take negation for this one. So none false. So none false, I should take what? Negation here. So negation of what? There exists x, negation of p of x. Next, second one. All false is negation of what? Not all false. So both of them are all false is negation of not all false. That's why from 4 I'll get it 2. So if I take negation gets cancelled, I'll get what? Every x negation p of x. Similarly, I'll take negation here also. So equal to what? Negation, there exists x p of x. So these four statements are from this I'll get these four. These four are equivalent. Next, rule for negating a statement covered by one quantifier. So to negate a statement covered by other than my voice, is there is any disturbance from here? Whether you are hearing, because there is some I think something is going on around my house. I don't know exactly what it is. They are talking.
No, sir.
Huh? I think no
No,
disturbance.
sir.
No disturbance.
Yes, sir.
Okay, thank you. It is disturbance for me. That's why I asked whether you feel the same thing. Okay. Uh, okay. Rule for negating a statement covered by one quantifier. Okay. So to negate a statement covered by one quantifier, change the quantifier from universal to existential or from existential to universal and negate the statement which it quantifies. So this is the procedure. For example, for every x p of x, what is the negation? Replace for every by what? There exists and put negation before p of x. Similarly, there exists x p of x. Replace negation for this one is what? Instead of there exists, you should put what? Every, and then we'll put negation before what? Whatever it is here. So this is the way you can get the negation of a statement. Okay. So next, we consider the following four statements. All cats have tails. No cat has tail. Some cats have tails. Some cats have no tails. So if the inverse for the statement, okay, well, if suppose we assume that if the inverse of the statement consists only of cats, so nothing other than cats, then this statement is merely the first one. Which statement? All cats have tail. You can write for every x p of x, where p of x such that x has what? A tail. So this is enough. When this is enough, if the universe contains only what? The universe consists of only cats. However, we know that the universe consists of objects other than what? Cats also. Objects, some of which are not cats. So a further refinement is necessary. So what is the further refinement? So first you should write C of x such that x is a cat, P of x has a tail. So additionally you have C of x is a cat. Now for the first one, all cats have tails. So you can write for every x, C of x implies what? P of x. Okay, you can see here. For all x, if the first one, the ninth statement, this is the ninth statement. For all x have tails means for all x, if x is a cat, then x has what? A tail. And it can be written as we are writing what? Universal quantifier for every x, C of x implies what? P of x. Next, the statement 10. What is the statement 10? No cat has tail. So no cat has tail. So if statement 10 means for all x, if x is a cat, okay, then x has no tail. Okay, so that is the meaning. No cats have tail means actually it is a cat, but it has no tail. It can be written as for every x, C of x implies what? Negation of P of x. The students may be right, no cat, so that's why they put what? Negation C of x. That is wrong. So negation C of x means it is not a cat. Okay, but it is a cat. It does not have a tail. So does not have a tail means you should put negation before what? P of x. Again, 11. What is 11? Some cats have tails. Okay, so some cats have tails means 11. So there is an x such that x is a cat and x has what? A tail. So this can be written by there exists x, C of x. You don't put implies. Okay, because if it is a cat, we know that for all cats have tail means okay, you can put what? Implies. But here only some cats have tails. So x is a cat and x has a tail. So C there exists an x, C of x, and that cat have what? Tail. 12th one. Some cats have no tails. So there is an x such that x is a cat. So x is a cat and x has no tail. So and negation of P of x because it does not have a tail. That's why I'll put negation before what? P of x. So now these are the four statements. So corresponding symbolic form, what we discussed here. And also mention what is C of x. C of x means what? X is a cat and P of x means what? X has a tail. Actually, these four, 1, 2, 3, 4. These fours are symbolic form here. So similarly, write each of the following in symbolic form. Assume that the universe consists of literally everything. Okay, all men are Jains. No men are Jains. Some men are Jains. Some men are not Jains. So you can define M of x, x is men, G of x, x is Jains. So all men are Jains. So similar, actually here what? All cats have tail. So all men are Jains mean for every x, M of x implies what? G of x. You can see here. Okay, wow. We assume that the universe consists of objects, some of which are not men also. So that's why I write M of x, x is a man, and G of x, x is what? A giant. So now statement A. Statement A is in the previous slide. All men are giants. That means for all x, if x is a man, then x is a giant. So you can write for every x, M of x implies what? G of x. Statement B. No men are giants. So no man, he's a man. Okay, well, for all x, x is a man, but he is not a giant. So it can be written as for every x, M of x implies what? Negation of G of x. So not giant. Okay. Now, next statement C. Some men are giants. So there exists x, M of x, and what? G of x. There is an x such that x is a man and x is a giant. So there exists an x, M of x, and what? G of x. The last one, some men are not giants. So there exists an x, M of x, and not giant. X is not giant, so that's why negation of G of x. Okay, so these are some of the formula equivalent statements. Okay, so you can easily remember this. I will tell you how to easily remember these four. There is no need to, I think, if it is necessary, I will tell you these are needed or not needed. Okay, so the first one. Okay, sorry. First one. So I will take this negation inside. Suppose if I take this negation is inside, so then this there exists is changed into what? Every. So negation of negation gets cancelled regard P of x. Similarly, I will take this negation to inside, that means before P. So instead of there exists, you can write what? Every, and then put negation here, negation P of x. Similarly, from here, negation. If I take negation inside here, for every x, you can write what? There exists, and negation of what? P of x. And then here, if I take this negation inside, so for every is changed into what? There exists x, negation of negation gets cancelled, you get what? P of x. Okay, now I'll go to the theory of inference for predicate calculus. Actually, these here rule US means universal specification. Rule UG means universal generalization. Rule ES means existential specification. Rule EG means existential generalization. So there are four rules. Okay. So here the same thing. Rule US. So I will explain here and then I'll go back to the definition. So something is true. Okay, for every x. Okay, then you can write it is also true for what? P of A or P of B. Okay, because it is true for what? Every x. Okay, so that's why this is called universal specification. Okay, and then rule ES. There exists an x p of x. So p of x is true for some x. Then you can write p of a, but on condition a is not used in the argument earlier. And then rule UG. UG is just opposite to rule US. So P of X is true for arbitrary X. P of X is true for arbitrary X of the inverse. Then you can write for every X, P of X. That is called rule UG. And then rule EG. We know that P of C is true, but I don't know about P of B or P of D. Okay. So in this case, you can write there exists X, P of X. So these are the four rules. So that is given in the paragraph. If a statement of the form for every x p of x is assumed to be true, then the universal quantifier may be dropped. This universal quantifier may be dropped from the statement to obtain p of x, which is true for each object in the inverse, or to obtain p of b, which is true for a specific object of the inverse. Even you can write p of x, just you can write p of x, or you can write what? P of b. Next, the statement p of x is true for arbitrary x, of the inverse. Okay, then the universal quantifier may be prefixed to obtain p for every x p of x, provided that every existential object in p of x, okay, uh, in p of x which depends on x is covered by the quantifier. Okay, provided that every existential object in p of x, very good, okay, which depends on x is covered by the quantifier. Okay, so what it means, suppose the statement p of x is true for every x, then you can write for every x p of x. The only thing is we should check the existential quantifier which contains p of x, okay, should be already, you should you should write that statement already before this. So provided that every existential object in p of x which depends on x is covered by a quantifier. Okay, we will discuss in the problem this one. If you suppose, if you don't understand, there exists an x p of x is assumed to be true, then the existential object b can be used to represent the object for which p of x is true, provided b is not already used to represent some object in the discussion. Okay, so next, existential generalization. If, so let it c be an object having a given property, and let p of c be a symbolic expression of this property possessed by c, which may or may not contain other symbols in addition to c. That means we know that p of c is true, but we don't know p of d or p of b is true. I don't know. So in this case, you can write there exists x p of x. So I think this slide is enough. Okay, in this slide, everything is explained clearly. Okay, so verify the validity of the following argument. Okay, all men are mortal. Socrates is a man. These two are premises. Therefore, Socrates is a mortal. So h of x is a man, because here they are using m. Okay, So m of x, x is what? Mortal. And then Socrates is a name. That's why I'll use a small letter s, small s. It's a Socrates. So now we show that all men are mortal. For every x, h of x implies what? M of x. For every man is a mortal. And then you can put and or you can put comma. Socrates is a man. Socrates, S means what? Socrates, H means what? H of X means what? X is a man. So if H of S means what? Socrates is a man. Therefore implies Socrates is mortal. So M of S. Socrates is mortal. Okay. Now, now solution or argument. I'll take the first premises for every x, h of x implies m of x. And I'm going to use the rule US. Okay. Here you can write h of a implies also m of a, but already used s, Socrates. That's why I'll write what? Because this is true for every x. That's why I can write what? H of a implies m of a, or I can write h of s implies m of s. But here you should write what? Rule US under number one. And the second premise is h of s. Now we know that p comma p implies q is what? Q. So that's why I'll get what? M of s. So that is the final solution we need. So thus the inference is what? Valid. Verify the validity of the following argument. Lions are dangerous animal. First premises. There are lines. Second premises. Conclusion. Therefore, there are dangerous animals. So L of x, x is a line. D of x, x is a dangerous animal. So first premise, lions are dangerous animals. So that means all the lions are dangerous. That is the meaning. So for every x, L of x implies what? D of x. And there are lines. So that means there exist lines. There are some lines. So there exists x, L of x. Therefore, there are dangerous animals. The conclusion is what? There are some dangerous animals. So there exists x, d of x. D of x means what? X is a dangerous animal. Okay. Now, first I will use there exists x, L of x. This premises. From this I will write what? L of b, or you can write L of a. No problem. They will write L of b. ES, rule ES, and using 1. Next, second premises. For every x, L of x implies D of x. Premises, second premises I am taking here. Now, this is true for every x. So that's why it is true for what? Particular b. So L of b implies D of b. Rule US, universal specification, and using 3. Okay. Now, from 2 and 4. P comma P implies Q is what? Q. So we'll get what? D of B. Now I got D of B from using 2 and 4. But I got 2 from there exist. I got 4 from every. So 5 is I got from combination of there exist and every. So that's why from 5 to 6 I can put only what there exist. Suppose this is also every, this is also every means I can put what here what every. So that this one I got from every, and every means I can put every. Suppose this one I got from one every and one there exist means you should put there exist. Both of them are there exist means always that is also there exist one. Okay, so now from 5 to 6, you should write what? There exists x, d of x, rule e.g., existential generalization, and 5. So I got it, this one. There exists x, d of x, thus the inference is valid. Okay, so next one, verify the validity of the following argument. Every living thing is a plant or an animal. Okay, next. John's goldfish is alive and it is not a plant. All animals have hearts. This is the first premise, second, third. Therefore, conclusion: John's goldfish has a heart. Okay, so here, let the universe consist of all living things. So this is most important. The universe consists of all living things. So we are dealing only about what living things. So that's why there is no need to write L of x is a living thing, because the universe consists only of what living things. Okay, so maybe some students are asked in the class, so why don't we write L of x is a living things? Because we are dealing only about living things. There is no need to write separately, because universe consists of all living things. Okay. Next, P of x is a plant. X is a plant. A of x is an animal, and then H of x has a heart. X has a heart, and then small g because name. Already I told that for Socrates I use small s. Similarly for John's goldfish, the name. So I'll take what small g. So every living thing is a plant or animal. So for every x is what? A plant. X is a plant or here R, that's why I'll put R, animal, A of x. Next, second premises, John's goldfish is alive and it is not a plant. So again the students will confuse here a little bit, because John's goldfish is alive because of this. Okay, this will make you little bit confused. Okay, and it is not a plant, because we are dealing only with what living things. So John's goldfish is alive is redundant for us. Okay, this data is redundant because the universe consists of what we are assuming the universe consists of all living things. So that's why this will not make an impact in the premises. Only it is not a plant. So you should write which one is not a plant. John's goldfish is not a plant. So G means what? John's goldfish. Negation of P means what? P means plant. Negation of P means not plant. Okay, next. All animals have hearts. For every x, A of x implies what? H of x. For all animals have hearts. Okay, already similarly, all cats have what? Tail. Similarly, we discussed what? One more thing. All men are what? Giants. Okay. Similarly, all animals have hearts. So for every x, A of x implies what? H of x. Therefore, John's goldfish has a heart. So John's goldfish means what? G. So G. H means what? X. H of x means x has a heart. So H of G means John's goldfish has what? Heart. Okay. Now we will use one by one. First, for every x, P of x or A of x. So this one. From this, okay, next I will take the second premise is also negation, P of G. Okay. Next from 1 to 3, I got it. I got 3 from 1, because this is true for every x, and hence it is true for what? Particular G. because G is already I am going to used here. That is John's goldfish. Okay, that's why I'll write here also G. So P of G or A of G. Next, from 2 and 3. So that means what? Here what? P or Q. Here have negation P. So you should write what? This part. So okay, P here negation P means here have R. Okay, so here A of G. So from this can easily write what? From 2 and 3 A of G. So this is also a rule. Okay, now fifth one. This is rule P. Rule P, for every x, A of x implies H of x. For every x, A of x implies H of x. Okay. From this rule US, this is true for every x means for particular G also it is true. A of G implies H of G. Now P, comma P implies Q is what? Q. So that's we need H of G. So thus the conclusion is what? Valid. Okay. So maybe we'll discuss one more problem. Give an argument which will establish the following validity of the following inference. All integers are rational numbers. Some integers are powers of 2. Therefore, some rational numbers are powers of 2. P of x, x is an integer. R of x, x is a rational number. S of x, x is a powers of 2 or power of 2. So now, first all integers are rational. So for every x, P of x implies what? R of x. Some integers are powers of 2. So there exists x integers. So P of x, P of those integers are what? Powers of 2. That's why I'll write what? And S of x. So the conclusion is therefore some rational number, there exists x, R of x, which is what? Powers of 2. So R of x and powers of 2 means what? S of x. So I will use the first premises for every x, or you can write first this one, P of x and S of x. Okay. Yes. I'll use there exists x, P of x and what? S of x. So rule P, and from rule ES, I'll write P of B and what? S of B. Next, P and Q implies what? P, comma Q. Second premises, for every x, P of x implies R of x. This one. From this, we have from using rule US, I have P of B implies what? R of B. Now, P, comma P implies Q is what? Q. Finally, we need what? R and S. So that's why S of B is here and R of B is here. So P comma Q implies what? P and Q. P comma Q implies P and Q. Okay. R of B I am getting from R of B and S of B I am getting from the combination of what? There exists and every. So that's why I'll put finally there exists. From here to here I'll use what? Rule EG. So there exists x, P of x and R of x. You can see here this one I am getting from every, but R of B I got from where? From 3 and 6, but 3 I got from where? 2, 2 I got from where? 1. So there exists. So that's why 8 is I got from combination of there exist and every. So that's why I put there exist x. I think there is a typo maybe here. Here we'll check it. There R and S. R and S. So or here it should be s. Sorry. Okay, there's a typo. So s of x. This is s of x and r of x. Okay. So we'll discuss two more problem and then I will finish it quickly. Verify for every x, p of x implies q of x. This is the first premises. Second premise is there exists y, p of y. Conclusion is there exists z, q of z. Okay, so first I will use this premises. There exists y, p of y. This is rule p, and from this I will write p of a using rule S, US, ES, existential specification. Next, this premises. For every x, P of x implies what? Q of x, rule P. Now from here to here, I use rule US because this is true for every x, so that's why it is true for what? Particularly A. So P of A implies Q of A. Now P comma P implies Q is what? Q. So Q of A. So I got Q of A is again a combination of what? There exists and every. That's why I'll put what? There exists Z because that is I need. Yeah, there exists Z Q of Z. So from 5 I got this one and using rule EG. Last problem. So there is a mistake in the following derivation. Find it. Is the conclusion valid? If so, obtain a correct derivation. So first one, for every x, p of x implies q of x. Rule P. So from here to here, I use rule US. So I'll write p of y implies what? Q of y. And then again, third step, I use the another premises. There exists x, p of x. From 3 to 4, they will use the rule ES. So they'll write what? Again, p of y. And then p of y comma p of y implies q of y. They'll write what? Q of y. I got q of y is a combination of for every and there exists. That's why I'll put what? There exists x q of x. That is rule EG. Actually, there is a mistake here. So what is a mistake? The y introduced in step 2 is free. That means this is true for every x means this is true for y or anything you can put it here. So that's why the y introduced in the step 2 is free. It should not be introduced again by ES in the fourth step because this is true for some particular x. So again, you cannot use the same variable here. So we try to eliminate this mistake by obtaining correct derivation. So better to use there exists x p of x already. Okay, first write that one. That is rule P. And then write P of y using ES. I will write what? P of y. Or you can write P of A or P of B. No problem. And then write this premises for every x p of x implies q of x. This is true for every x. I can put the same y here, but the other way is not possible. Okay, other way means here I use for every x from here I will write y. There exists x p of x. Maybe this y is true or not, need not be true. So that we don't know. So that's why to avoid these types of mistakes, first I will write there exists x p of x rule P. From here to here, rule ES. And again, third step is rule P. And from 3 to 4 is what? I applied rule US. I'll write, because this is true for every x, so P of y implies what? Q of y. So now P comma P implies Q is what? Q. I got Q of y from combination of what? There exists and every. So that's why I'll put what? There exists x q of x. So this one I got from 5 and rule EG. Okay. So thus there exists x p of x. This is and for every x p of x implies q of x implies what? There exists q of x is a valid statement. Okay. I'll stop here. The remaining problems we'll discuss tomorrow. I think okay, we'll start from worked example 7 tomorrow. Okay. Thank you.